Hi everyone, my name is Ryan and welcome to CS188 exam prep number 4. Today's topic is going to be MDPs and I'm just gonna dive right in. So for the first question right here, we have a casino game and the objective of the game is for the player to earn some sort of money. And essentially how the game goes is the player rolls a fair six-sided die right here. And then the die can land on either values 1 through 6 with an equal probability distribution. Each roll costs $1, and the player must roll the very first round. Additionally, we have two different actions that we can take for playing the game. We can either stop, where we essentially collect the dollar value that the die has landed on. So for example, if the die is 5, we would collect $5. If the die was 6, we would collect $6. And the other option is to roll, where if we roll, we can pay an extra dollar, so we lose a dollar, but then we get another chance at getting a higher score. And once again, we collect money eventually based on the final reward that we roll. And so we tend to model these types of problems as an MDP. And usually what happens with these kinds of exam level problems is just we ask you to compute it, we ask you to figure out some equation for it, and all that good stuff. So for the first part right here, we are considering using policy iteration to determine the optimal policy that we can eventually converge to. And in general, with this case, we start with some sort of policy right here, so pi of s, and then we assign a policy value or action to each of the states. So as you can see right here, each of the states we've initialized with some sort of like option that we can take. So roll, roll, stop, 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 stop. So yeah, and what we want to do right now is evaluate the policy at each state where gamma is equal to 1. So what does that mean? Well, evaluating the policy just means given a specific action, we want to compute the value associated with that action. So in terms of an equation, what that would look like is something like v pi of some state s, which is the value of the state given a specific policy, is going to be equal to the possible transitions that we can go to from taking that action. So if we consider the action of a specific state to be pi of s, which is the policy or the action from the policy that we associate with the specific state s, then we have to take into account the transition probability of going to any other state s prime. And then we're going to multiply that with the reward that we get for going to that next state. So r of s pi of s prime, and then plus the discount factor gamma times the value of the successor state. So in this case, we have v of pi s prime. So this is essentially the equation that we want to run for all of these different states that we have. Now, because of how we set up the problem, you don't really have to like go through this equation, but it's good to keep in your mind. So for starters, let's consider the reward we get for these states where the optimal policy is stop. So recall that based on the problem description, if we stop, we just collect the number of dollars that we are at based on like the roll of the die. So at S3, we would get $3, at S4, we would get $4, etc. So essentially, if we evaluate the policy at those states, we would just get 3, 4, 5, 6. And we don't need to consider the other case because we're just evaluating for a specific policy. We're not really taking into account the other policies right now. Okay, so now that we're done with that, let's consider the value that we get in the case of S1 and S2. And just for convenience, I'm going to move this equation a little further up. Okay, so recall that when we roll the die, what we do is we pay $1 and then we get a new roll value based on some sort of distribution. And in this case, we have a uniform probability distribution. So we would just have 1/6 times the value associated with any possible successor state. So note that when I roll the die, I can get anything from 1 through 6. So for each possible roll, let's consider the value at state 1. In this case, what I would get is the reward, which is -1, which is the reward of taking that action. So it's the cost of taking the action of rolling. And then we would need to add this with gamma, which is 1, so I'm not going to include it, times essentially each individual successor state. And basically, because of how this works. Our transition model, right, is our T of SAS prime. That's going to be 1/6 for each possible successor state we could get. And overall, that's just 1/6 times the value of each successor state. So I'm just going to have 1/6 right here. And then that's going to get multiplied by each value summed together. So if we think about like just expected value, we have v pi of s1 plus v pi of s2 plus, and then we would have to consider v pi s3, s4, s5. But because we know we've already evaluated v pi of 3, 4, and 5, I'm just going to write plus 3, plus 4, plus 5, and plus 6. All right. So this is an equation that we want to be able to solve. And similarly, we can set up another equation of the sort for v pi s2. So for v pi s2, we can do the exact same thing where we have -1 reward plus 1/6 times v pi s1 plus v pi s2 plus 3 plus 4 plus 5 plus 6. Because if you notice, the expected reward that we would get for each of those would be the same because we're just rolling the dice and we could get any outcome, essentially. Okay, so now that we have these two equations and we have two variables that we want to solve for, we can just use a system of linear equations to solve the problem. I won't bore you with the math, but essentially, if you multiply it out and then work it out, you eventually get v pi s1 is equal to 3, and v pi s2 is equal to 3 as well. So as you can see, the expected value of rolling essentially is going to be 3. All right, cool. And I'm just going to write this down here for clarity. V pi s1 equals 3, and v pi s2 equals 3 after solving. Okay, great. So let's move on to part B. For part B, we have the same policy that we had before, but now we want to consider if we should update our policy after we have evaluated our policy. So this is like the next step when we do policy iteration. And what we want to do is essentially compare the value that we got, or the values that we got up here at the very top, with the values that we would potentially get if we were to consider the other action instead for our optimal policy. So let's take a moment to think about it for a second. We know that stopping always gives us the reward associated with the state number, right? So if I were to stop from any of these states, I would get 1, 2, 3, 4, 5, and 6 respectively. Well, we also know that based on what we saw above, rolling always gives an expected value of 3. It doesn't matter what state we roll from because that's not considered in our calculation. All we care about is like the potential outcomes that we could get from taking that action. And in this case, that means that rolling is always going to give us a value of 3 for our value, given our current setup. Therefore, we can consider that any state that is greater than or equal to 3 will benefit more from stopping versus actually rolling again. And consequentially, any state that's less than 3 will benefit more from rolling. Therefore, if we just like look at the state numbers, we can observe that rolling is better for 2. Rolling and stopping are the same for 3. And then stopping is better for 4, 5, and 6. All right, cool. So part C is asking us, okay, that policy that we had before, that we started with, is it optimal? So based on our iteration of our policy, what we saw is that when we updated our policy or tried to update our policy, we noted that it didn't change. And in that case, since it didn't change, we know for a fact that the old policy is optimal. So even though there's like a tie right here, essentially it could be either or. Both would be the action of the optimal policy. And basically, the new policy is as equally good as the old policy. And so that means by definition that policy iteration has converged. Therefore, we could say it's optimal because policy converged. Okay, and for the last part of question 1, suppose that we're now working with some arbitrary gamma from 0 to 1, so just like within the valid range of usual gammas, and we wanted to run value iteration. So in this case, we want to select the one statement that would hold true at convergence. And this is a similar setup to what you would normally see in these kinds of problems, where we would ask you to kind of just like craft a function based on the problem description. So what do we know about this? We know that the value or the v star of any state Si is going to be the maximum of one or two things based on our setup. It's going to be either the maximum of taking action roll or taking action stop. So we want to consider how much value we would get at for each of these cases. So if we consider the value at every state, we know that we have a maximum and we want to take the maximum of first stopping. In the case that we stop, we get value equal to the index of the state, right? So in this case, for Si, if we were to stop at this current state, we would just get value I. Now for the case where we roll, we have to consider how potentially how much value we could get from rolling based on like a summation of the different successor states that we could go to and the values of those states, as well as like the whole transition function and that sort of thing. So recall that when we roll based on the problem description, we get a reward of -1, which is our incurring cost of taking action roll. And then for each state, for each possible state that we could go to, we have a 1/6 chance of getting to that state because we have a fair die. So we have 1/6. And then we would have to sum over all the different possible successor states values that we could potentially have. So if we consider the set of all possible successor states to be J, then we would be summing over V star of S underscore J. And then recall previously we didn't have a discount factor. Our discount factor was 1, but this time we do. So we also have to multiply this expression by the discount factor gamma. So in this case, because the problem writes it like this, I'm also going to write the gamma on the fraction, but it doesn't really matter. And so yeah, this would be our value function given the problem description. And this is guaranteed to be our optimal v value for any state Si. And based on the problem choices, if we just like analyze which one's the same, we would get this. All right.